I'd like to introduce to you the concept of particle diagrams. Here's an example of a particle diagram from biology, before diffusion and after diffusion. So you've been seeing particle diagrams in textbooks and online and throughout your entire science career. Here's another one that we have used in chemistry class. This is taking a look at mixtures and pure substances, elements versus compounds. You can see here that these particles are different colors as well as different shapes. If you're wanting to test yourself, you can try to remember what these represent, but here's the answers. We've got a mixture of two elements, a pure element, a mixture of an element and compound, a mixture of two different compounds, a pure compound, and a pure element. So this is just another place that we've used particle diagrams. Here is further in depth in chemistry. We talk about nuclear chemistry, where we actually look at the particles within a nucleus. So you can count these particles in the nucleus, and then an alpha particle, this is called alpha decay, comes out of the nucleus. This here is called nuclear fission. Same thing, we're looking within an atom to those particles, which brings me to the first conversation about particles. What is a particle? Well, really the definition of a particle is a little bit loose. It just means kind of a small thing, right? So when I'm talking about particles and I'm talking about those particles being distinct and countable, I may be talking about atoms, I might be talking about compounds, I might be talking about inside of an atom, protons, neutrons, electrons. So the word particle loosely describes something that's small, all right? So these are the rules that we use. We need distinct and countable particles. We want to remember that different substances have different particles. Particles are represented in the correct physical state, and correct physical state would mean solid, liquid, and gas. If it's possible to represent these, you want to be representing these. Obviously, with nuclear fusion, this isn't something that we're talking about very much. And then lastly, if possible, you're going to do a before and after scenario where mass or matter is conserved. So if you can kind of keep these general rules in line, and I did put rules in quotes here because none of these are set in stone because all particle diagrams are different, you will have a better chance of having a nice particle diagram. So I'd like to show you here a basic particle diagram. Here I have a sugar cube, and I took the sugar cube and put it in water. So I like to start with kind of a before and after scenario of my sugar cube in water. So before I have water, and then after I'll still have this liquid. All right, so I'm going to want to represent the water as something. Now, I'm going to choose to represent the water as blue circles, okay? Um, Now, believe it or not, afterwards, the water is still there. So the same blue circles are going to be there. And this is where I come up with the conservation of mass. I would like this to be countable. I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. I can't have a water molecule just pop out of nowhere. So I want to make sure I have the same number of water molecules in my before picture as I have in my after picture. In my before picture, I also have sugar. So I'm going to change the color for sugar because I can do that pretty easily on my iPad here. And you can see my sugar is in a nice solid block there. So I'm going to represent it as a solid blocks or a solid block. And I've got 9 sugar particles before and then after. They're going to dissolve in the water. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is again a very simple particle drawing of what would happen when sugar dissolves in water. As you get further on in chemistry, you might realize that sugar is made up of carbon, hydrogen, and oxygen atoms. So you may be representing that in your particle diagram, in your before and after. So the cool thing about particle diagrams is that they can grow with you all the way from very basic chemistry all the way through AP chemistry. Let's go back to my melting water example and make sure I did it correctly. I had a before scenario and after scenario. I tried to show my ice cube as a solid 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And my ice cube has kind of melted. So I've conserved mass before and after. If you think about chemical reactions, or what we call stoichiometry in chemistry, you can think about things that are going to react together. So here I have a compound, whatever it may be. This might be a carbon with hydrogens. It may be something else. These may be oxygen molecules. I don't know because I don't have what we call a key on the side here. All right, so in order to have a good particle diagram, sometimes, or really all the time, you should have a nice key here. And I should say that the black circle represents carbon in this case, and that the gray circles represent oxygen. That would help for me to realize that this is a combustion reaction. And if I were to go through and count this, I would see I have 6 hydrogens and 6 hydrogens, or 12 hydrogens. And after the combustion reaction, these are hydrogens attached to oxygen, also known as water. So this matter has been conserved. So this is showing us stoichiometry here. It's showing us that we have C2H6 plus O2 yields CO2 plus water. And again, that's a little bit more advanced. You can see here, here's a couple other representations. This one is going out of its way to show you that we've got gases turning into different gases. You can see here, maybe this is a liquid with a gas over it that's turning into a different liquid with a gas over it. I'm not sure. There's some reason that whoever drew this went out of their way to make something that's layered. So finally, I just want to bring home to you that particle diagrams, like I said before, can grow with you, right? If you're just starting out, you may see a candle burning particle diagram as, showing you've got the candle and it's got countable particles in it, and we don't really know what a candle is made up of. And sometimes people will even draw the pictures there. But then afterwards, I know that the candle starts to melt and something starts to happen and the candle starts to disappear. So the wax goes out into a gas. All right, this would be an extremely simple representation of combustion. But the more I know about the chemistry, the more I can add in, the more I can say, well, I know I've got oxygen that is hanging around in the air. And I know that that oxygen is going to react with the candle wax. And even if I don't know the exact chemical formula, I can still start to make predictions with my particle diagrams. Over here is a Bunsen burner. It's burning methane. You can see this is showing complete combustion. This is actually incomplete combustion. If we wanted to get into details, we could also show that in the particle diagram. And finally, the last thing I want to show you is that particle diagrams can show us movement of particles. So I can show that gases are moving by showing arrows. I can show that they're moving slowly, or I can show that they're moving quickly. I can show that they're bouncing off of the wall. There's other things that I can do to show movement of my particles, which is something that you'll be able to include in your future of particle drawings.